name is Matt Scott, and I am super excited to talk to you guys today about deep image retrieval, techniques, and application. So this is a talk that will be targeting towards computer vision students, but those who are, would like to have an introduction to image retrieval. We will begin the talk in just a minute. I would like to say that all questions I will be answering at the end of the presentation, so please mark them down and I will address them. And we are about to begin. So, today's talk is going to have two major aspects to it. The first are the techniques. I'm going to introduce from a beginner's point all the way up to some modern techniques using deep learning for image retrieval. And then I am going to introduce an application, a real-world large-scale image retrieval system. And then at the end we can learn more about the technology and the company. Alright, so let's dig deep now and get into deep image retrieval techniques, starting with a definition. So the definition of image retrieval is actually different from instance retrieval. So image retrieval here is just given an image query, I would like to rank all of the similar images, get the rank of most relevant images. So for a image, I am not going to be specific. In an image retrieval sense, if I am searching for a dog, maybe not this specific dog, I am expected to get any kind of dog output. But instance retrieval, which will be the majority of this talk, image retrieval for instances is a bit different. So instance retrieval is all about finding this dog or this particular object and generating a rank list of all images containing this particular object. So that's what we're going to be speaking a lot about today is instance retrieval. And now we're going to go over the basic retrieval pipeline. This is a common pipeline that we will be referring back to for this talk. So let's start from the beginning. In an image retrieval pipeline, the query image is provided where we get image representation that is in a vector format. It's a format that we will be able to compare with other images in the data set. Now, in the data set, we refer to those images as reference images, and we will be in the back end extracting features from those images in such a way that we can enter the image matching stage, the filtering stage, which is where we apply a similarity metric. So the vectors, these vectors will be compared against one another. I want to highlight for you guys that really the key point here is really all about image representation and how we can rank these images when we compare them. So our goal really is to find a global, compact, rich representation for each image. And then once we reach the similarity metric stage, when we filter the images, we'll be applying one of several common similarity metrics. For example, cosine similarity, finding the angle between the vectors, Euclidean distance, dot product, which is very fast. So something very special here I want to highlight is that there are multiple stages in a typical image retrieval pipeline. The first pass of image retrieval is sometimes referred to as the filtering stage. Now this is a stage where we go through all of the images in the data set and we apply somewhat of a fast check to all of them, and we'll get back a large number of potential candidates. And this is the candidate list. We can call it also a ranking list, where we will apply more expensive operations, computationally expensive operations to help filter the items. So we often refer to this as re-ranking. But in the sense that I mentioned before, that we're going to be focusing on instance retrieval, spatial re-ranking is the flavor of re-ranking that we will be preferring. So, query expansion is another form of optimization that we will be talking about in just a bit. But after we apply these optimizations, then we get the final results. So that's the basic retrieval pipeline, and now we will go deeper inside. So let's talk about spatial re-ranking. So we're going to be starting at the end of the retrieval pipeline here. So the end of the retrieval pipeline, we are going to be talking about this spatial re-ranking. So given a ranking list from the filtering stage, we're going to re-rank, and then we will be getting better results. So what is spatial re-ranking? Okay, so in the back end, when we are actually indexing these reference images, remember the reference images are the images in the data set, we will be applying some algorithm to extract regions from these images. These regions could be plentiful. We can find many, many regions in these images. And the way we calculate or determine these regions I will discuss in just a bit, but the main idea for spatial re-ranking is that once we have the ranking list after the filtering stage, maybe you have the top 100 or the top 1,000 images, there's an expensive operation you can do where you can take the main object from the query, which has been identified through could be through various means, that object or that region in the query image. For every region in the list that we get back from the filtering stage, for every image, for every region within those images, we will compare the similarity between region to region. Now, by doing this, we will also, in a sense, automatically get a rough localization just by this checking. So that's the basic idea here for spatial re-ranking. Once we look into each of these images, we find the key objects, and then we can get a much better ranking. Now I want to describe very briefly how we can build these region proposals. So there's several common ways. So one common way is something called selective search. Another common way is RPN, region proposal network. And even a more simple way is just a rigid grid. We just can, sliding window, go through and extract out different regions. And now you may be thinking, wow, this sounds pretty good, but it sounds pretty computationally expensive. No problem. Later in this talk, we will discuss how we can make this faster. All right, and let's talk a little bit about query expansion. Now, a bunch of people probably have heard of query expansion. It's a very common trick to improve, a common technique to improve the quality of the search. So, but I want to make a distinction here between global query expansion and local query expansion, just like I made the distinction at the beginning between image retrieval and instance retrieval. So for the entire image, what you can do for global query expansion is you can it's an image level representation. So for the top n, usually the top 5, we will take those results that came out of the pipeline, which have the feature vectors, and we will pool them together in some way. Typically, we will average those feature vectors together, and then we have a new query representation that we then re-query. So it takes 2 queries. Now, usually the results are much better if we're going to be doing an image retrieval task. So, but there's something I want to distinct here about local query expansion. Local query expansion is related to the regions. So just like I mentioned before about spatial re-ranking, the idea is that once you've selected the most likely regions in the ranking list, you can collect those most similar regions, and just like you do for query expansion at the global level, at the local level, you're just going to average those vectors together and form a new query representation that you can then re-query, and the results are typically much better. So now let's get more into the heart of the matter here. the heart of the matter is really all about image representation. So now I'm going to the sort of the front of the retrieval pipeline. Let's talk about image representation. So I'm going to start from the traditional aspects of image representation, and then I'm going to go forward into the modern era. So typically in traditional image representation, we would use some handcrafted features, for example, sift or hog, or many different kinds of handcrafted features. Now, what happens when we run these descriptors is that we get back many key points. And these key points are all feature vectors. So, and you can see here with this panda, you get n feature vectors back per image. But remember, the goal of image retrieval in the pipeline is I need a single global, compact, rich feature vector. But here, I've got many feature vectors. So how am I going to combine them together or deal with them to produce a final feature vector? That's really what we're talking about here. And I want to plant this flag now that the lessons we learn here, we're going to still refer back to them in the future part of this presentation. Okay, so here's the common technique. BOW or BOVW is called Bag of Visual Words. Bag of Visual Words is it's inspired from NLP, a bag of words, where we can do search with using linguistics. So here we're going to be coming up with a vocabulary, visual words. Now, how do we build visual words? So the first step we're going to do is on the reference images, we're going to build this vocabulary. So we're going to go through all the reference images, and for all the key points, we're going to put those vectors into some d-dimensional feature space, and then we're going to cluster using typically k-means to do the clustering. And typically k is a very large number, 50,000 or more words you can think of. And then we're just going to find the centroid for each of those words, and we're going to find the nearest match for each feature vector. So each feature vector will basically be assigned a centroid, and then we're just simply going to count which the number of the accumulation per centroid. And then what we've got here is quite a sparse representation, but it is a single feature vector, but it is quite inefficient to search just as is. So we can use these traditional techniques like inverted files to make the matching much quicker. For example, by finding the matching words between different images. There's a lot of techniques you can do. And then a more advanced technique is VLOD. VLOD descriptor. It's actually the vector of locally aggregated descriptors. So it's quite similar in some respects to the bag of visual words. It's that we will be collecting a bunch of, just like the bag of visual words, we'll be collecting a bunch of feature vectors, and we're going to be running some kind of clustering on those feature vectors, typically k-means again. But the difference here for VLOD is that unlike bag of visual words, k is usually quite small, usually around 64. So you may be thinking, well, if it's only 64 words, there's going to be a lot of collisions. These are not this is not very discriminative. So what we can see here is there's an additional aspect, of course. It's the residual. So the residual is actually just the difference between the feature vector and the centroid that it is that it is matched to, that it is assigned actually. So this residual gives us quite a lot of useful information. So if we sum up these residuals, then we can get this VLOD representation, which is actually pretty good representation traditionally. And again, I want to plant the flag that we're going to be referring back to this topic later. So let's move on. So now we're starting to get into deep learning. Now, I'm showing you here a a architecture. This is the most famous architecture. This is just for reference. This is AlexNet. And when people started working on deep learning for classification, they did notice that if you take one of the last layers, the fully connected layer, and you just treated it as this feature vector, it actually works pretty well. It's a reasonably good representation of the image. So typically this is something people have been doing, several years ago, but there is a better way. Let me explain what's wrong about using the fully connected layer. In fact, there's nothing absolutely wrong. It's just generally there's better ways to go. So when you use the fully connected layer, what's happening is you are losing spatial information. The spatial information is lost at this stage. So many algorithms that rely on spatial information are not compatible with this information. Another problem of using the fully connected layer is that the input image must be stretched to typically to a square size, so that will actually distort some of the features. So these are some of the issues using this. And again, I want to highlight here that I am just using the AlexNet as a reference, but you can take the similar concept to all modern deep architectures, including VGG and others. So let's talk now about the more modern approach to image representation with the convolutional neural net. Using the last convolutional layer, for example, on AlexNet, that would be Conv5. And what we do here is that we'll notice that we have a volume of activation maps, and it turns out that this is a pretty good representation for the image. In fact, it's the state of the art as a baseline for your representation. Now, the problem here again is that just like we saw before, and this is why I introduced it before, we don't have a single feature vector at this point. We have a volume. So we have many feature vectors, and we need to combine them into a global feature vector. So how can we do that? And so here we have notes that you can pool them together. And let's talk about this pooling because it's so important. Let's talk about how we build these descriptors. So when I say descriptor, sometimes this is also a feature vector, different way to say it, global feature vector. So the image representation and the region representation is typically we found through experiments that there are better ways to represent them. You can use the same pooling method, but typically we found for image representation, summing up across the dimensions is better than max pooling. And so let me describe some of the mechanics here. So we will be taking each feature map and pooling the entire slice. So the entire slice here, we will just take the sum, for example, for image representation, or for region representation, we just take the max number. And then we build a feature vector according to the dimensions that we have here. And what's great about this is that the feature vector is always the same size, no matter the size of the image, and the image is not restricted to a square size. It could be any size. So this is typically what we found works pretty well. So let's formalize this definition a little bit. So the formal definition, we can call it as a MAC, maximum activation of convolutions. So we can apply the image as the MAC, and here we'll find that if we take the entire image, and again we'll go to the last convolutional layer, we will be able to then sum pool. We'll be able to max pool according to the dimensions and produce this final n-dimensional feature vector. Now, where it gets more interesting is RMAC. RMAC is the regional maximum activation of convolutions, and what's interesting about this is that we will be taking the same concept that I just mentioned, but we will be applying it as a region within the feature map, and we will cut through the feature map according to the D dimension, and we'll just slice right through, but only applying max pooling to that region. Okay, and so we'll be able to figure that out by mapping the region from the query or the reference image back down to this feature map. And there's different ways to go about coming up with the region. So you can, again, use rigid grids as region, which is more of a systematic approach to coming up with the regions. But again, the key point here for RMAC, which I will be mentioning in the future of this presentation, is that RMAC can be a very good representation for instances within objects within the image, and by cutting across the activation maps in the last convolutional layer. So I just described a way to achieve using the last convolutional layer, but there's other ways. So the good news is that there is no one way to go about things here. There's a lot of options, and now we can be inspired by traditional computer vision. Traditional computer vision has decades and decades of wisdom that we don't need to just throw away. We can learn from the past and apply some of the best practices. So here, and again, just by applying the best practices doesn't imply that it's actually the best way, but it's just another way. So here we can use the bag of words technique that I mentioned before to pool together or to aggregate together the final feature vector that we can call the global representation for the convolutional features. And here's some of the mechanics about how that works. So we can take an image, and through for example, the last convolutional layer, again, we're treating this as a volume, 3D volume, where every component in this slice of the feature map, every component, if you go across lengthwise across the dimensions and you pull out each of these one-dimensional feature vectors, they become the local feature vectors that we can be somewhat inspired by with the past representations. And so now we've peeled off these feature vectors, and we can apply the same techniques we learned before, which is in the back end, while we're indexing or processing the reference images, we can apply a k-means. And again, we can use a large k, for example, 25,000 or more. And then we would apply, just like before, we would simply assign each feature vector to one of the centroids. And then we'd come up with the bag of words encoding, just like before, and then can use inverted files and other optimizations. So that's one way. And here's an interesting other perspective, is that we can use this representation for instances. So we can take a region of the image and apply the same mechanics to that, except that we would just count up the assignment map for that particular region. Okay. Now let's talk a bit about the slightly more sophisticated representation of a traditional technique called the VLOD again. But here we're going to be using VLOD for encode. We're going to encode with VLOD for these convolutional features. So here's how that works. It's actually a very similar technique. As we saw before, we treat, again, each convolutional layer as a 3D volume, and then we're going to peel off these feature vectors, and then we will be applying the k-means and assigning the centroids. And then we will be going ahead and calculating the residual. But there's something I really want to highlight to you guys now, because it'll come up later, is that for each of these feature vectors, we are assigning, you can call it a hard assignment. We're just assigning one centroid to each of these feature vectors. So that's something you should know for later, because that'll come up. And finally, after all of these processing, we will be able to come up with the VLOD descriptor, which again is the sum of residuals. So let's summarize so far. So far, I have been talking about how can you use off-the-shelf CNN representation. Here, I'm not actually talking about training a model for image retrieval. I'm going to be talking about that in the next section. So here is I'm just using a model that's already been trained for other tasks. Actually, for a typical pre-trained model for this task that we just described is typically done for classification. But we'll soon see that there is a much better way to go about that. So again, let's summarize so far. So far, the summary is that you can use traditional methods to encode the CNN activation maps, and sometimes it's better or worse. It really depends on what your task is. There is a process you do want to apply for each of these feature vectors before you actually want to use it in search. You will be needing, or typically found in the literature, to apply L2 normalization, PCA whitening, which will reduce the dimension because all of the feature vectors we've talked about so far are quite large. You're going to want to reduce the dimension, and then renormalize. Again, we talked about different similarity metrics like cosine, similarity dot product, Euclidean distance, and the decision for which of these metrics you use is really, again, up to your task based on your experiments and your requirements. So the other point we want to highlight here is that convolutional features are better than fully connected features from an experiment in general. And this is something that is important to keep in mind. Why are they better? There's a few reasons. One is that the convolutional features keep the spatial information. So this will allow other algorithms, for example, that perform localization that can use this information. And it could also work for instance retrieval, which is part of the topic that we're talking about for most of this presentation. And of course, convolutional layers allow for custom input size because they will be using the sliding window, not requiring a fully connected layer. So we talked about these models, and these off-the-shelf models, pre-trained models. They're good if you really don't have any data labels available and you don't have the resource to train. But if you do have data labels available, fine-tuning the network to the target domain does, in fact, improve the CNN representation in general. So we will now explore what it means to use training for image retrieval. So this is where it gets really interesting, and we're getting more advanced now in actually using deep learning for image retrieval. So we're going to be learning a CNN representation for retrieval. So let's start with the classic Siamese network. Now, what's interesting for when we're talking about retrieval, what's interesting for the Siamese network is that unlike a classification network, which a classification network is going to be learning a classification, but a Siamese network is actually going to be learning a feature space or a metric space that allows us to compare different feature vectors in a way that preserves their semantic distance. So, for example, a Siamese network, after we train a Siamese network, we should be able to find that images that are close in a semantic distance, in fact, are coming up close in a numerical distance that we calculate. So this will allow image search to work, image retrieval to work really well. So how do we train a Siamese network? Well, first of all, you can see on the right side here, we will provide two patches to a Siamese network, and we'll provide a parameter that specifies, are these patches the same thing or not? 1 or 0 is the parameter. And the loss function is going to be, I will describe what the loss function is on the next slide, but the basic idea here is that we have two convolutional networks, CNNs, and we're going to be sharing the weights between these two networks, and the output is the feature vector. And we'll be comparing this feature vector, the Euclidean or L2 norm, and then we're going to be trying to minimize the patches that are the same, and we're going to try to make the patches that are not the same have a far distance from one another. Okay, so let's talk a little bit about the loss function. So we're talking here about contrastive loss. So basically, if the training sample is indicating that these two patches are the same, then we're simply going to be minimizing the distance between them. And if they are not the same, then we're going to be trying to maximize the distance by at least some margin, m, as one of the parameters here. So this, in effect, will create a great place for us to search for our target domain. But it could be better. So Siamese network, it does a good job, but there are ways to improve it, and I will be discussing that here. So to improve a Siamese network, we can discuss triplets. So triplet loss. This is now more of the modern way to go about this. So why are we in need of a triplet loss? Is because you can see on the left side of this diagram here, sometimes, just because you extract the features of an object doesn't necessarily, mean that the negative example is further away from the positive example. So on the right side, you can see for face verification tasks, we can find that the images look quite similar. So A stands for the anchor, P is the positive, and N is the negative example, and they look very similar. So if you just use an off-the-shelf classification model, you're probably going to get features that are represented in the feature space that are actually not following what your expectation is in terms of negative and positive nearby the anchor. So our task here is to learn it. So we're going to be providing 3 streams to this network, and the output expected is that the negative examples will be further away from the anchor and the positive ones will be closer. So this is a better way to go about such a thing than the Siamese network, although the Siamese network can provide, you can indicate a positive pair and a negative pair, but by providing all of them at once, it does give a better result. And we can see at the bottom of this chart here, we do have the very similar looking loss function. So again, we're going to be using the distance plus some margin, and we're going to make sure that, again, the negatives are at least some margin away. Okay, so now we're going to, throughout this talk, I'm going to keep combining concepts that we've already discussed. So now I'm going to combine RMAC, our good friends RMAC, the RMAC representation, which again is the maximum activation of the convolution, the region-based, and we are going to be combining that with the triplet loss. So previously, there was an assumption that when we extract the features from these triplet loss or Siamese networks, we didn't exactly clarify what features are we using, what descriptors are we using for this. But when we're talking now about RMAC, we're being very explicit that we're using an RMAC representation with triplet loss. And if you use this together, we found that there are better results. So I do want to make a point at this stage that for the data set, although you will get better results most likely, the cost in acquiring such high quality labeled data is quite cumbersome, and we'll discuss some methods to deal with that later. Okay, so now we're going to be describing here an end-to-end training for learning this triplet loss with RMAC. RMAC is one choice, but we do recommend RMAC. So if we look at these two boxes here, the first box is the training architecture, and the bottom box is representing the deployment network. For example, we'll be testing on this network. So for the training, we have provided the query or the anchor, the relevant or positive or irrelevant or negative, and we will be using some region extraction or region proposal method here. So again, you can use various methods, but we found that using the rigid grid is totally fine. And the next stage in this process here, and again, I want to highlight what's really special here, is this is an end-to-end training. We're going to be learning two important things. We're going to be learning a feature representation, and we're going to be learning a metric space. Okay, so let's go through this network briefly. Just like the Siamese network, we have convolutional layers that we have weights that are being shared. And then we enter the ROI pool, region of interest pooling. We will be preferring, again, to use the RMAC representation. Then we enter the normalization. Next few layers are normalization layers that we described at the beginning, which are common. The common normalization, again, is L2 normalization, PCA and whitening, and L2 normalization. But how do you do PCA in a training when you train end-to-end? I mean, you know, PCA is not very good. You can't train with it. I mean, it's not going to be working in this way. So we have a method to approximate PCA, which is applying a shift, which is somewhat of an averaging, and FC, which is a fully connected layer. So what's happening here is this is, again, an approximation of PCA, and it works when we train end-to-end. And then we're going to L2 norm. And then the summation here is actually really important because this is actually really interesting, because before I mentioned to you how it's quite difficult to, when you compare image to image, region to region, that's actually a lot of comparisons. So a very key point here is that we found, and the literature also describes, that you just need to sum. You just need to sum up the RMAC results here for each of those regions. Just sum them up, and then L2 norm, and then you have a very good representation. And then we backprop after we apply the triple loss. So now, once we've got that, we have the weights we can load up for our deployment network, and then we can go from there. And the search becomes much better. So let's talk now. Let's bring back our old friend, Vlad. So NetVlad is what we'll be talking about here, which again is another way to do a convolutional neural net representation for retrieval purposes. So we all like Vlad, of course, but Vlad had a problem. So if you want to include Vlad in an end-to-end network, then you will have a small issue, okay? Because Vlad does a hard assignment, as we remember. When we assign the centroid, it's a hard assignment. So what does that mean? It means this is a non-differentiable function. This means that we can't backprop. Backprop is not going to work. So then it can't be embedded directly in the convolutional neural net and participate in the error back propagation. So what's the solution? Well, in this paper that we're referencing here, and again, a lot of the papers we're referencing are very recent. So this is sort of the modern techniques here. So the solution to deal with this hard assignment issue is soft assignment. And how we do it, we use our techniques, our mechanics from CNN, which is the softmax. We can use the softmax function to translate this hard assignment into a soft assignment operation. And we're going to keep using our mechanics from the CNN, which will be using the 1-by-1 convolutional layer, and then we'll be using the softmax function. We'll get the probability and the weights of the local features belonging to each center point, and then we'll be assigning it with which the greatest probability and weight to the center point. Thus, we have the NetVlad. And now NetVlad, it contains 3 parameters that can be learned. So the parameters, like I just discussed, are the 1-by-1 convolution above that we just mentioned, the predicting the soft assignment as well. And in this figure, we can see that we also have this Vlad core. So Vlad core, what Vlad core is going to be doing is it's just going to be operating on accumulating these residuals. So that's what the Vlad core is all about. And then we apply intra-normalization, which means we'll for each of these vectors that we've extracted, we'll do an L2 norm, and then we will stack them together, and then we will have a L2 norm across this entire this entire set. And then finally, we have produced the Vlad vector. So I want to also mention to you guys something really, really interesting, is that NetVlad it's not just applying original Vlad, it actually has some additional advantages. So for example, in the traditional Vlad, we talked about the clusters. So how we calculate the residual is we subtract the difference between the feature vector and the centroid of the center of each of these cells. But with NetVlad, we may optimize that. It's actually flexible to learn the centroids, and this actually can produce higher performance. So earlier I mentioned that triplet learning is really great, but there's generally a problem with triplet learning, is that it's a pretty high requirement on your annotations, on your labeled data. So in this paper, there's actually a very nice improvement offered here, is this concept of a weakly supervised triplet ranking loss. And now the concept here is that in order to solve the problem that training data may contain noise, what's happening here is the positive and negative samples in the triplet ranking loss are replaced by a positive sample set. So in the set, which includes at least one positive sample, but we're not very certain, and then we'll also have a set of negative examples. And so we can see here that the first stage in this ranking loss is that we're going to be selecting the best positive example. And the feature distance between the query image and the most likely positive sample in the sample set is going to be smaller than that between the query and all the negative samples. So that's what's happening over there, and that's a nice way to deal with perhaps noisy data, which is a common problem for supervised learning, of course. All right, so now I'm going to be talking about an interesting case that depends on what task you're working on, what resources you have, but in some cases you may have rich annotation data available, like really good data that has multiple aspects to it. So for this paper, this is a paper we'll be discussing that it's the deep fashion paper, and what this paper is introducing is if you have such rich data, for example, landmarks, for example, for fashion search, landmarks, and you have, of course, the categories, and then you have attributes related to those categories. Such rich data, this data actually can help boost each other. There's a greater effect, a higher performance that can occur once you have such good data. So I want to describe for you a little bit about how this works. So the author, Zoe, proposes a really nice novel network here, which it learns the most distinguishing features by jointly predicting the key points and attributes of close. So the overall framework for the network, it works as follows, as you can read from sort of left to right here. The forward calculation is divided into 3 stages. The first stage is, of course, the clothing picture is fed into the network. And we're going to be predicting the key points of clothes visible at this location, at the locations that they would be predicted at. And the second stage, of course, is we're going to be, according to those key points that we just received in the previous step to predict the location, we will be then having a key point pool layer. Here you can see the landmark pooling layer. And we'll be able to get the local characteristics of those clothes. So, you've heard me say again and again, local versus global. So local features. So by having these landmarks, the landmarks really can boost the efficacy of these local features. And so you see here some bit of complexity on the loss function. This is a multitask, so we have actually a bunch of different loss functions here. And the loss functions work as follows. There's four loss functions. So what we see here is that we've got a regression loss that corresponds to the key point location. We have a softmax loss that corresponds to whether the key point is visible and in the clothing category. There's a cross entropy loss function corresponding to the attribute prediction, and a triplet loss function corresponding to the similarity learning between the clothes. So this is a very powerful representation that we can get from here. So again, what we're learning is we're learning a feature representation, a very rich feature representation, and we're learning a metric space so we can compare. So in summary, for this network, the major takeaway here is when there is enough label data, deep learning can simultaneously learn more. Okay, you can give it more, and it can take advantage of it. It can learn features, measurement as well. So that's the basic idea of this network, and we can learn from that. So we've talked a lot about very advanced networks for image retrieval, learning for image retrieval. But now let's talk about some of the practical issues. So some of the practical issues is that, what do I get back? I've got a big feature vector of floating point numbers. Now, what happens if I have to search millions or even billions of images? You know, this is still a lot of data I have to deal with. How can I do this efficiently? So one of the common techniques to deal with this efficiently is to binarize the features. Why do we want to binarize? Because, of course, we have a very, very efficient method of comparison for distance when we're in a binary format. Of course, we have the Hamming distance. And why is Hamming distance so fast? Well, it's mostly just an XOR operation, which is incredibly fast to perform. So now, how do we want to go about binarizing the descriptor? You know, we can apply some simple threshold. We can do something more like learning a representation. Can we take advantage of a deep neural net, deep convolutional neural net, to generate this compact binary descriptor? So that's something we'll explore. And can we do this in an unsupervised manner? So on the right side, you can see what I mean by converting the features to binary. So let's talk a little bit of details about binarization, or having a binary representation. So again, if you just apply a simple thresholding or even somewhat sophisticated thresholding, you may deal with some issues because there may be some loss of the structure in the representation space. So one of the jobs here when we're trying to learn a really good binary representation is we're going to try to minimize the quantization loss. The quantization loss is all about preserving the structure so that we basically have a faithful representation in binary. So that's a very key point here. The other point that we're going to try to deal with is a distribution. We're going to be worrying about the even distribution of the bits. We don't want too many more. You know, in terms of probability, we don't want there to be a higher probability of ones than zeros. Actually, the problem there is actually what we're trying to do here is we're trying to maximize entropy. Because if we have less entropy, then we have a less performant representation. And the other aspect here is rotation invariance. So when we're learning a binary representation, we can actually learn rotation invariance as well to make the descriptor invariant to rotation and noise. So that's a work that's a very effective way to have a faithful binary representation that is that works at large scale and also extremely fast. So let's summarize some of the retrieval techniques here for the deep image retrieval techniques. First is I want to summarize and say that the pre-trained or off-the-shelf CNNs are useful for image descriptors. They have quite a few advantages. If you don't have the labeled resources or the training resources, you can just use a pre-trained network. It'll give you reasonable results, but not great results. Great results come from fine-tuning to actually learn. So convolutional features are great because they encode local information. And again, if you just use the fully connected layer, you're going to not have that local information. It's going to be lost. So if we can summarize, what's the primary task here in retrieval? It's really about rank similarity. We're trying to learn to know if a particular feature vector is close or not to in a semantic way. That's really the major point here. So the end-to-end convolutional neural net that learns how to rank, that's really the most desirable thing. Now, again, there is a bunch of requirements on labeled data and resources. So if that is available at different levels, we described different ways to take advantage of that. So again, you could use there's a weak supervision technique for triplet loss. You can also use if you have rich annotations, you can just use that directly. So it really depends on the task and the resource involved. And then finally, we talked a little bit about a practical issue on speed. And binary descriptors are really great, but learning them are even better, and they're extremely attractive for high speed. So those are the summary of the techniques. And now I am going to switch gears here and talk about an application. So we talked about techniques. Now let's talk about putting this together into something that solves real problems and is on is engineered to be sophisticated and large scale. So let's look at that. Now, before we talk about the application, let's motivate ourselves with the problem to solve. What are the problems to solve when we're talking about this application? So the key business problem to solve is that, well, many companies are out there that want to improve their products with deep learning and computer vision for image retrieval and recognition, but they don't have the resources. They don't have the know-how required to do it themselves. So there's thousands and thousands of companies out there with tens or thousands of millions of products, and how are they going to leverage this miracle of deep learning for their business? So what does it actually mean though for a scenario? Well, there's a bunch of scenarios you can consider, but one of the common scenarios is for e-commerce providers, like long-tail e-commerce providers, stock photos, or physical product companies, to enable retrieval on their products so that you can find the products in the product catalog so users can buy them. So I'm going to switch over to the right side here and show a video of just exactly this one of these scenarios. So let me go back here. Okay. So this is a fabric scenario, textiles. So in this demo, the users found the fabric that they desire, and then they can just go ahead and find the fabric in the store, in the e-commerce provider's catalog, and then they can just go ahead and purchase it. Very straightforward. Now, you can go to all kinds of fabrics. So actually, this is our CEO, Huang Dinglong. And here we can find Dinglong's fabric, which is a very handsome orange fabric, and then we can go ahead and purchase it. So this is a general scenario you can imagine for all kinds of companies that have products. They want to make their products available in this way. So what you just saw here, in fact, from this demo is actually one of our customers using our service, actually. So this is actually our application at an API level that they're leveraging, and then we'll look a little bit more into that. So what are some of the key technical problems to solve when we're considering the real-world application? So when we're considering the application that I described, you have a lot of different scenarios. But how do you build a single high-performance retrieval system that is still able to achieve high performance even across multiple orthogonal target product domains? Orthogonal, I mean very different target domains. So if you, as we just talked about all the retrieval techniques, say you learn a great retrieval model for textiles or materials, is that also going to be good for vehicles? Maybe not. So how do you sort of unify these things together? That's a serious challenge, and there is just a ton of different scenarios. And the idea is, can we really do all in one, or how are we going to do this? So the second significant technical problem is, how do you enable a large-scale system that work on ingesting, indexing, searching in sub-second time for just huge data, millions of images for thousands of businesses operating all independently on a single platform? I mean, that's a serious technical challenge and a serious effort. And this is some of the things that we worked on, and happy to talk about how we've approached it. So how we came up with a solution, and this is what I'll be introducing as the application, is what we call Product AI. And it's actually more of a platform. And let me tell you a little bit about the story to introduce or motivate what Product AI is all about. So at the beginning of the company, we first built a consumer product, a consumer product called Style AI that works on image retrieval and recognition. It's an application for fashion. And then something interesting happened, something we didn't expect. Many companies approached us and they asked us to enable this retrieval technology for their products. This was a reoccurring event, and we realized there is a tremendous value here to help other businesses. And so once we realized that, we decided to build a single cloud platform that businesses can go on and they can operate by themselves. At the beginning you think, well, maybe we should handle each case one by one, but it becomes cumbersome. So we wanted to make a system that customers can just independently work on getting their image retrieval and recognition services tailored, to their data. And so we've got that going for image retrieval here. So we built this for a single cloud platform. Customers can work independently, and we go way beyond fashion. Fashion is just one of our core and a very great scenario for us, but we do go beyond fashion into many other product domains. So hence the birth of Product AI. And so you may have heard the slogan, AI for your product. And so for this audience, let's just translate that to deep learning and computer vision for your product. And what it is, it's a self-serve system. So again, customers can work independently. It's large-scale retrieval and recognition API platform. So customers can upload their information, their data, and then the system can analyze it and produce a custom API for them to address the specific needs of specific industries to improve their products. So let's talk about some of the technical approaches, the high-level technical approaches to go about some of the problems we described. So what we do to deal with the performance issue is that we don't try to build one ultimate model. Okay, we actually deal in this way. We break it down by verticals. So we train high-performance image retrieval models in the particular vertical. So this is a matter of technology, also a matter of requirements. Each vertical, is special in its own way, and we need to adapt to those verticals. So we use the latest techniques, of course. Some of the techniques we described, some of the techniques we also invented ourselves, and we then perform them, again, on a per vertical industry basis, and that's the concept here. So we create this concept of scenario selection, which allows the user to select the scenario that they are desiring, and the system, the platform, will then load those industry-specific models that can best detect domain objects and extract features from the reference images and queries for those domains. So how do we deal with the performance issue is that we use a bunch of the previously mentioned, aforementioned techniques, and we also utilize distributed computing techniques. We enable efficient indexing. We search across elastic number of compute instances, and we heavily optimize our models. That's a major piece of our work, is how to make the models run extremely fast. And we utilize GPUs even at inference time for where necessary for high-speed testing. So to make this very clear, this application very clear, I'm going to run through a little bit of a demo for you guys, so it'll hopefully solidify some of these concepts. So what we've got here is it's a web portal, just like you can sign up for Azure or Aliyun or AWS. You can sign up, and let's see here. Let's lower that. Okay. So once you sign in, you see all the different features that the product AI can offer. And we have a really interesting concept here. The concept is the data set. So once you produce or create a data set, you can reuse this data set against different scenarios. So first stage, let's build that data set. So here we are going to build a data set for clothing scenario. So clothing search. E2 Soso, and we name the title. We're going to give it a little note, and let's go ahead and build that. So now we will create the data set. So we're going to upload. We have different ways to populate the data. Here we used a CSV file, which has just a bunch of URLs in there and some metadata. And now we're going to do the very important operation, which is to apply a scenario to this data set. And so we're going to describe what that scenario is. So this is, again, the clothing search. And you can see here that we actually had a bunch of different scenarios that we selected. So I'll just drop it back a few moments here, just so you can see. You can see here, at this time we have a bunch of different product scenarios, and for each of these product scenarios we've developed high performance models to work on these scenarios. So let's just skip ahead, and now after we've said okay and we've created our service, it's going to enter a processing stage, and then we're going to re-log in a little bit later after the images have been processed, features have been extracted, models have been built, API has been deployed, and now it's ready. So here it's ready. It's once you have your API ready, you can just go ahead and you have a nice testing interface here. So I'm just going to go ahead and click the testing button. And you can see a bunch of the API information. You do see a secret key here. Don't worry, that secret key is invalid at this time, so no worries about that. And let's try that again. So here we go. All right. So now we are testing the service. We're going to provide a testing image, and we can see the results. So we've analyzed this object, and we've come up with the matching semantically similar results here. Very easy to use. Customer, again, simply needs to upload photos, select the scenario, then they get a custom API. These are the JSON results. We give a very professional JSON response. We also provide example code in several different languages, and we'll be adding more. And it's extremely easy to use to integrate into customers' products. Now that was the platform for image retrieval, and we also have a bunch of different image recognition services. So here we can see we provide these image recognition services because they're complementary to the retrieval scenario. So for example here, we've selected, since we just built a service for fashion, we also have complementary recognition services. So here it's a service for detecting the style. It's a classification model for style. So here we're going to be looking at this Japanese photo here, Japanese style, and we're going to be providing it here to this testing interface, and we can go ahead and see what the system says, and we can see the tags that it's produced and the JSON, and we can see here the probability, the score that it's Ruben is pretty high, so we can go ahead and accept that result. So more and more of these complementary recognition services are being added now. Okay, and I'm running a little bit low on time, so I will just zoom past here. So I just wanted to show that we can do other, of course, scenarios. So this was a material scenario, and it's very similar to what you just saw. And here we can provide materials, and we'll get a very good retrieval result. So again, our technique here is we sort of go very deep on these different industries, and the fabric industry is a very big user of product AI, and they have determined it's compared to others, it's at the highest level. So people are using this more and more, and we feel very happy about that. So this is our real world application for image retrieval, solves real business problems. And then I'll just zoom by here and show you here in this demo view we have a bunch more recognition services, and here this is one of our other scenarios you may have saw is furniture. So here is just a furniture detector, a very high quality furniture detector, and more similar scenarios. All right, so let's now get towards the end here and just talk about what's next for product AI for this real product. So what's coming up next is we want to solve more problems for more industries. So you saw already a bunch of scenarios and a bunch of features that are useful, but we want to keep solving more and more, and we're talking to more and more industries right now and going deep on them. The other thing we want to say that's coming next is the AR and AI support. So we believe that AR, augmented reality, is the best possible experience for AI. You just look and you get. So we're providing support for that because customers are telling us they want that for their products. Their products can be enhanced in certain scenarios, for example, marketing scenarios. It's really engaging an AR experience. And core tech achievements is something we're going to keep working on. We're going to keep advancing our core tech, making the models are more accurate and work faster. So I want to give you guys a little treat here of something that is not yet on Product AI's platform, but it does use our core technology. And this is a scenario that's actually a real scenario, customer really using it, really benefiting from it. It's a customer that is going to be using a soda can product and building a augmented reality scenario. So let's have a look at this. So we can see that the can was recognized using Product AI, and then an AR experience is generated based on the return values, and then it goes into a gaming mode. So you can be very personal with your products. You can make products more personal by understanding the products visually and providing an AR experience. Okay, so that's just about it, but I do have one more thing to talk about. Just one more thing. We're hiring. So we are hiring. Marlong is hiring, and so a bunch of people in the audience here are just the kind of people we want to talk to. I just want to mention a few things about our company here, and I'm sorry for the advertisement, but it's a good opportunity. So Marlong, we are looking for you. We are looking for research scientists and interns very seriously. We're, again, a well-funded, fast-growing AI startup. Some of the data points here are, you can go ahead, by the way, and scan this QR code, and you'll get more information. So we are a round, 62 million RMB, just closed our A round. We've increased our value 4 times in 18 months. Our industry-leading packages. We're really at the top of the pack here. We have a really strong and growing business. We're really making money with AI. Our offices are available in Shenzhen and Beijing. We also have a Tsinghua University joint AI lab, so we officially are working with Tsinghua University, and we have also with the Shenzhen government, we have developed an actual academic institution. So for those in the audience listening now who are interested to join industry, but you still love publications in the academic world, and you want to keep your publication record and your academic credentials, well, one thing Malong can offer is this joint AI lab, which is, again, it's an actual research institute that you can keep up all of that. And it's, again, in a official collaboration with Tsinghua University. We also have a world-class team. You can see our team having fun in the photo above. Actually, we see many beautiful people in this photo. Exciting work. We work on really interesting and hard problems, problems that really make value for the industry. And it's really great to sort of work on a model and then see it deployed and see the benefits used economically, and also see how many people can use it. It's really fun. And we do have a bunch of resources. So we have a lot of fun here. We have a bunch of unique large-scale labeled data, and we have abundant number of GPUs. We just got a whole lot of batches of the new Titan X Pascals, a lot of great technology, a lot of great resources here. And so we encourage you, if you're interested, to say hello, send your CV at the hr@malongtech.cn, and if we are a match, we'll fly you out here to Shenzhen, and we'll have a nice chat. You can come by the seaside. It's a beautiful experience here. So thank you guys very much. And now I am open to questions. 谢谢大家。谢谢大家的鱼丸。